name is Diana Hooper, and I'm a postdoctoral researcher currently at the University of Helsinki, where I'm studying all of the cool things happening inside the universe. And let me just change the screen here. I always forget that I can't see comments and the present on screen at the same time. So my name is Diana Hooper. I'm a postdoctoral researcher over at the University of Helsinki, where I'm studying cosmology. That means that I study the universe, the contents of the universe, everything happening inside the universe, how it all interacts, how it all evolves, basically all of the fun things like what is going on inside the universe. It's a great topic. I love talking about cosmology. I love talking about science. And I love jumping here on Haps and chatting to everyone about all of the cool things happening inside the universe. Hey, David, great to see you. Thank you for joining. So, today's the first day I'm actually going out to my YouTube channel as well. Oh, thank you for the love celebration, David. I do appreciate the words. So today I'm going out to the YouTube channel as well. So you can watch me on YouTube, on Twitch, on Twitter, or on Haps. You can join in the conversation in all platforms except Twitter, because Twitter have turned off their comments on live videos, which makes no sense. So if you want to join the conversation, head over to Haps, YouTube, or Twitch. I'm DC Hooper 91 on all socials, except on YouTube, where you can find me under Cup of Cosmology. More on that very, very soon. So, I like coming here and chatting to everyone about all of the cool, amazing things happening inside the universe. Now, obviously, it's a broad topic. There's a lot to cover. Like, there's so much going on inside the universe. Where does one even start? So it's fun. There's a lot to study. There's a lot to talk about. And yeah, this is a place where you can ask any questions you have. Hey, you're not really late, Scott. You're like 2 minutes in. Come on, you're still on time. I know Haps is still buggy. You can follow me on other platforms as well. For example, there's now a YouTube account associated to this, and you can follow me on Twitch as well. And then you're more likely to get notifications, because unfortunately, all of the notifications on Haps are not working so well. Hey, Paul, you're from YouTube. Thank you so much for checking that. I really appreciate you checking. I can see your comment coming in from YouTube. I should technically also see any comments coming in from Twitch as well. So wherever you're watching from, all of your comments do come in here together. So I can see your comment on YouTube, Paul, and thank you for checking. And thank you for subscribing to the YouTube channel. I do appreciate that. So before I get into too much detail today about the topic that I have sort of prepared, hey, David on Twitch, nice, thank you for checking. So we've got people on Haps, we've got people on Twitch, we've got people on YouTube. We're covering all bases now. At some point, maybe a Facebook page will appear, but probably not, because Facebook, Meta. No. So for now, YouTube, Twitch, Twitter, Haps, these are the places you can find me, and very soon. Big news coming. So this is the last stream on the current format of Cup of Cosmology. So next week, I'm doing a big relaunch. My streams have been going on for over 6 years now, and it's about time they got a bit of a makeover. So next week on Sunday at the same time as now, I'm doing the relaunch of my new streams. So you can still expect similar things. I'm still going to be here answering questions about the universe, bringing up cool guests, chatting about fun topics. The relaunch is more with the idea of new content. It's going to be easier for everyone to interact with me. It's going to be easier to request topics. Then, for example, if someone were to request blue dwarfs, it would be much easier to actually get me to talk about that. I know we've covered that topic by now. So next Sunday, we're doing the big relaunch. There's going to be a new web page. There's going to be a YouTube channel, which today I'm trialing out the YouTube channel, but the YouTube channel actually goes live properly next week. It's going to be easier to find my old content. It's going to be easier to find the highlights, the best things that have happened on my show. So I'm super excited about it. It's a lot of work. A lot of work is going into this, but I'm super excited to share this with you next week. So I am committing to the relaunch happening next Sunday, 8 p.m. my time. So yeah, 6 years, right? Incredible. Yeah, I started streaming in August 2015. So it's 6.5 years ago that I actually started my streams. It's impressive to me to think that I've been doing this for 6.5 years. Of course, there have been a couple of months where I've taken a break. There was a pandemic going on. I moved country when I finished my PhD. I did take a couple of months break, but my first stream was over 6.5 years ago, and here we are, still going. So it's about time I had like a proper makeover and started doing things properly. So yeah, next week will be 1 year since I joined Haps. So next week is the perfect time to do the relaunch. I'm super excited to share it with everyone. I'm playing about with it like constantly right now, and I'm really excited to share everything with you all next week, assuming I finish everything on time, which I should. So next Sunday, big relaunch, new stuff coming, new content, more guests. I already know who's going to be the first guest on the new show. So it's going to be really cool. So really looking forward to sharing that with you all next week. You've already seen the logo. There's going to be stuff happening with the logo as well. I love my new logo. So yeah, as always, just that little teaser side. As always, I'm here to answer any questions you have about the universe, about the contents of the universe, anything you want to know about what's life like in academia, whether I recommend academia to people. Any questions, this is your chance to ask away. I will try to answer any questions people have. Also, if someone could give me some feedback regarding the lighting, because I'm actually trying a new setup today. I finally got lamps installed here, which means I'm back to my webcam, which I bought specifically for live streaming. But today I'm testing the setup for the first time. So let me know if the lighting is good. Let me know if the audio is good. Let me know any feedback of anything I should change on my side, because I want things to look good for the relaunch next week. Thank you. Lighting looks good. Thank you for that comment, Scott. Hopefully it is good. Switch here to Haps to see Scott's jokes. Yeah, the thing is, if you join on Haps, you can see everyone's comments. So if you want to follow Scott's bad jokes and all of the fun stuff happening, you want to head over to Haps, because that's where you will be able to see all of the comments. But I know Haps does have some bugs, so don't worry about it. Follow me on whichever platform you want. But if you come over to Haps, you will get to see more of the comments here. I just saw I got an odd bot here. Okay, that's nice to get bots. Audio is better than before. That is good. It should be, because I'm now back to using my camera, my webcam and microphone setup that I actually bought specifically for live streaming. But I've had an issue the last few months where I haven't actually been able to use it. But now I think I've got everything sorted. And I think the lighting is good, the audio is good. There is one annoying thing, that the light is right behind my computer, which means I see all of the dirty stuff on my glasses. And there is something that is really bothering me, so I just need to get rid of that. And now we can continue. I can just see stuff on my glasses, very bothersome. Okay, so there might be some new people in here. Your jokes are not bad, Scott. We do appreciate your jokes. They're bad, but in a good way. There might be some new people watching who found me on Friday. So Friday, 2 days ago, I did a really, really fun webinar for the iTelescope network. It was really fun. We had about 200 people join. I gave basically a lecture, and I thought it was super fun. And we had so many good questions. I think we got 90 questions in the Q&A, and I was only able to address like 55 of them. I was talking for about an hour after the webinar. It was basically like a lecture followed by a HAP stream. It was a really, really fun. So if anyone's found me thanks to the iTelescope network on Friday, welcome. Welcome. This is the place to carry on asking all your questions. Is that Van Gogh's Starry Night behind me? Yes and no. It's the exploding TARDIS done in a Van Gogh style from an episode of Doctor Who. So it is Doctor Who, but also Van Gogh influence. And I love that poster. It's actually not mine. It belongs to my partner, but I kind of acquired it, and it moved country with me. It came to Finland with me, so it's basically mine now. But yeah, I love having this nice poster behind me. So as always, feel free to ask any questions you have. In the meantime, I'm going to start talking about stuff that I want to talk about. And from the title, I've actually started giving my streams titles instead of just generic, let's talk about the universe. So I've made progress there. Today, I want to talk about structure in the universe. Just going to say this up front, I am not talking about alien structures. I'm not talking about an alien megastructure potentially orbiting Tabby Star. None of that. I'm talking about actually how galaxies fit together in the universe and why there are galaxies instead of there being no galaxies. So in order to talk about structures in the universe and why there are galaxies and why there's a cosmic web, we're going to tell a story that starts in the very, very early universe. So I'm going to go back to the beginning of time itself. It sounds so dramatic. So we're going back to the beginning, or as far back as we possibly can go. I'm going to tell a story that starts then and ends or continues up until today, going through my favourite thing, which people will know what I'm getting to there. And I'm going to tell you why there are galaxies in the universe today. So in the early universe, the universe was really, really, really small. It was so small that it was governed by quantum effects. Now, quantum effects is a fancy way of saying that everything was vibrating, and I just realized I forgot to get out my Slinky toy. Today would be the perfect day for my... Where is my Slinky toy, actually? Today would be the perfect day for my Slinky toy, but I actually have no idea where my Slinky toy is. Anyway, in the early universe, everything is governed by quantum effects. Once upon a time, as David says in the comments, there was a tiny universe. Very, very tiny universe. Now, when we say quantum effects, it just means that everything is oscillating. And if you have an oscillation, you have a wave associated to something. So in the very early universe, you have a lot of these waves. Now, these waves have maximum and minimum, which we call like mountains and valleys or peaks and troughs, depending on how you like it. But we have these high points and low points. Now, quantum jitters, I like that term, quantum jitters. It sounds much easier to understand than quantum effects, quantum fluctuations. So they're quantum jitters. And as a universe, so in the very early universe, we believe there was a period known as inflation. Now, during an inflation, the universe expanded exponentially. It went from being a very small, tiny, hot thing to being a very big, slightly less hot and slightly less dense thing. Now, inflation is something that is not yet proven. It's our best working model, but it's not yet at the level of being as good as other parts of cosmology. It is a very, very nice theory, but we are still missing some observational evidence for inflation, but it is the best picture we have so far. I think if I were around then, I would still think it was infinite. Yes. Yeah, if you were around in this tiny, insignificant little universe, you would be scaled down to size as well. So as the universe expanded, everything in the universe moved away from everything else, and things got stretched. One specific thing that got stretched is the wavelength or the waveform of these quantum fluctuations. And this is something that we actually are used to more in the universe today. Like anytime we talk about redshift is what we mean when we say an object is shifting towards the red end of the electromagnetic spectrum. Objects that are moving away from us are redshifted, objects that are moving towards us are blue shifted. Now, the idea of redshift, I'm going through different steps here and then I'll backpedal it. The idea of redshift is very similar to the Doppler shift. Now, the Doppler effect is what happens if you hear an ambulance coming, for an example. Now, based on the noise that the ambulance is making, you can tell whether the ambulance is coming towards you or moving away from you, because the sound wave is either getting pushed in front of the ambulance or is dragging behind the ambulance. So you have this different noise as the ambulance is coming towards you and as it's going away from you. Some people pronounce exponentially as exponentially. Really? I've not heard that. Well, as long as we understand what we're talking about, it doesn't matter how people pronounce things. As long as we understand each other, it doesn't really matter. Everyone can pronounce things however they like. So, and I'm using that as an excuse for when I mispronounce things. So, you've probably all seen this effect that when an ambulance comes towards you and when it moves away from you, the sound is different. So this is just because the sound wave is either getting squashed or stretched. Now, light waves do the same. So light waves in the universe, if they're traveling towards you, are going to be slightly squashed and shifted towards the blue end of the electromagnetic spectrum, whereas light waves that are moving away from you are going to be slightly stretched and pushed towards the red end of the electromagnetic spectrum. Now, in the same way that sound waves can be stretched and compressed and light waves can be stretched and compressed, the waveform of these quantum fluctuations could experience something similar. So in the early universe, we went from having these tiny quantum fluctuations with a waveform, and these expanded. As the universe grew, these waveforms expanded. This means that once we're at the time after some point after inflation, which is when we can actually start doing proper calculations, there's a very American comment there, and I'm going to go on a slight sidetrack here. Comment from Scotty of when an ambulance comes towards me, I hear the sound of thousands of dollars leaving me. You should not have to pay to get an ambulance. The medical system in the US is broken. You need healthcare for everyone. It's not a difficult concept. Europe has figured it out. Healthcare is not perfect in Europe, but we are a damn sight better than the US. Anyway, not gonna go too political too far on that, but yeah, sort out your healthcare, guys. Does gravity's pull ever become an equilibrium if you place the human on a neutron star? Immediate death, obviously. Great question. So I like that question. Now, the gravitational force can actually be balanced out, usually by other gravitational forces. Now, of course, if you go to a neutron star, it's going to kill you, it's going to suck you in, you're kind of going to be splattered on the star. You would have some cool spaghettification and cool effects happening there, but you would basically be splattered. But you can actually balance the gravitational force with more gravitational forces. One clear example of this is what we do with a lot of satellites. You can actually place satellites in a place where the force coming from the sun and the gravitational force coming from the Earth cancel out, and there is no net effect on the satellite. So it's basically in a stationary orbit, in a place where all of the forces cancel out. And this is, for an example, where we sent the Just Wonderful Space Telescope out to Lagrange 2. It will reach its destination tomorrow. Tomorrow, the JWST is actually going to reach L2, the Lagrange point 2, which is where it's going to be in this stable orbit because the gravitational forces are balanced out. You're welcome to come to Europe, Scott. in a lot of countries, you wouldn't even need to learn a new language if you speak English. So an orbit is a sort of equilibrium, gravity versus momentum. Excellent comment there, Scott. So yeah, when we are in orbit around the sun, when an object is in orbit around the Earth, what this means is that you're actually in a place where you're not falling constantly into the sun, you're in equilibrium. And here you have the idea that the angular motion is counterbalancing the gravitational force. So you can actually counterbalance the gravitational force somewhat. So yeah, counterbalancing the gravitational force is something that we have seen happen in the universe. Now, it's quite hard if what you want to do is to create like an anti-gravity where you don't feel the gravitational force. Then it gets a bit hard. But you can actually feel those. If, for an example, you can cancel the gravitational force by taking an elevator upwards. You feel that kind of lifting where you're cancelling the gravitational force because you're being lifted upwards. Or if you're in a plane that suddenly goes into freefall, let's hope nobody's in that situation unless you want to be and it's intentional. If the plane is in freefall, you get this zero-G effect where you're counterbalancing the gravitational force by some acceleration, which is also cool. Back to the topic at hand. Don't worry about getting me off topic. It's fine. I'm always happy to go off topic. So do keep the questions coming. I do like the questions. So, yeah, of course, we are in a rotating frame of reference with the Lagrange points. Absolutely. There's always the thing of which frame of reference are we taking and absolute motions and stuff like that. Right, so we have these quantum fluctuations in the early universe. As the universe expands, these are stretched. Now, the cool thing about this is that when we start our equation sometime after inflation, we have what we call some initial conditions of the universe, and these are what tell us what's going to happen afterwards. Now, you can either get the initial conditions from inflation or from whichever theory you prefer to inflation, but you need some initial conditions. And what we actually have at some point after inflation, so at some point in the very, very early universe, we have regions of space-time that are more dense than others. So I'm not talking now, hey, Jan, it's great to see you. Glad you could join. Hope the trains weren't too much of a hassle. Glad to see you here. So, yeah, we have these quantum fluctuations that have been stretched in the universe. What this results in is areas of space-time where there is more density than other areas. So right now I'm not talking about matter because this is before matter actually formed. This is just really in the early universe. And this is something that we technically call the metric fluctuation, which basically means it's regions where space-time itself has more density than other regions. Just on a side comment here, if you have a really, really dense region of space-time, it could hypothetically collapse into a primordial black hole, which would be a black hole that was born in the early universe without a star, which is super cool, but not the topic for today, just leaving that there for future reference. So you have these regions of space-time where there is more density than others. This means there's going to be regions of space-time where there's a slightly stronger gravitational force than other regions, because you have the metric of the universe itself create, or the universe itself has these pockets of density and underdensity, overdensity and underdensity. Okay, so early universe, we have these metric fluctuations. Now we have stuff happening. We have particles beginning to form. We have dark matter appearing. We have a lot of stuff happening. Now, in the very early universe, dark matter is going to break away from everything else. It's going to stop talking to all the other particles, if it ever talked to the particles at all. It's going to stop doing that, and it's going to break away. Now, at this point, the dark matter is going to fall into these metric fluctuations, into the region where there's a bit more density. So the dark matter is going to start settling down in these places where there's a stronger gravitational presence. So now we have the picture. We have these quantum fluctuations that left little valleys and mountains in the fabric of the universe. We have dark matter starting to fall in the valleys just because it's more energetically favorable, and the universe doesn't like spending energy if it doesn't have to. So dark matter is settling down into the valleys. Now we fast forward a bit. Dark matter is just sitting there doing its thing. Let's look at what else is happening in the universe. So now I want to stop the picture around 380,000 years after the end of inflation. A bit of stuff has happened. We formed some of the first really nucleus. We formed some protons. We've got some helium nuclei going around. But the really interesting part for me starts 380,000 years after the Big Bang. Now at this point, the dark matter is in the valleys. And, of course, the dark matter is going to gravitationally attract everything else, which means overall, all of the particles are more or less going to start piling up in these valleys that were formed by the quantum fluctuations. People who know me well or know cosmology know why 380,000 years. What are we doing with this number? We know this number. It's my number. You know what I'm getting at here. So we have these valleys and mountains formed by the early quantum fluctuations, which are stretched. Dark matter is piling into these valleys. It's gravitationally attracting everything else. And when I say everything else, there are three main components at this point, apart from the dark matter. We have protons, we have electrons, and we have photons, which are particles of light. So I swear this is not just an excuse to throw the CMB at you. We are leading up to structures. So we have these three particles, or not only three, we have these three species. And in these three species, we have the protons, the electrons, the photons. Now, they're constantly bumping into each other. The photons will bump into the electrons bump into the protons. There's a constant interaction. But as the universe cools down and expands, it becomes energetically favorable or energetically efficient to create hydrogen. So the protons and the electrons will combine together to form neutral hydrogen. And at this point, the photons, the particles of light, can't bounce into anything else. They can't bump into the protons and the electrons anymore. So the photons break away and they start traveling freely throughout the universe. These photons have been traveling freely ever since. But there's one important thing here, that these photons first have to either escape these valleys or they're already on the mountains. Now, coming back to this, regarding the immense voids, does this mean there is no density at all, no dark matter? So it's not that there's none, it's just that there's less. So if you imagine that you have you take a wrapper from open a piece of candy or some chocolate, you get the wrapper, you crinkle it up a bit and just ignoring the noise that's making, then you have these kind of valleys and folds, you have this structure. Now imagine you throw rice grains over it, or salt, let's use salt, I'm improvising this analogy, you throw salt on top of the wrapper. Now most of the salt is going to fall in the creases of your paper, but some of it will still be on the places where you have a hill. If you shake it, it's all going to go into the void, into the valleys. Now, of course, you're not really shaking the universe. So in this idea here, where you have your candy wrapper or your piece of paper crinkled up and you've thrown salt over it, overall, you'll see that the salt falls into the valleys, into the creases, but you still have some on the top as well. The same is true in the early universe. A lot of the dark matter, a lot of the particles are going to fall into these valleys, but you will still have stuff on the mountains as well. So it's not going to be completely empty. Now, it becomes really significant when these photons break away. Because if these photons break away and want to start traveling freely in the universe, the ones that are at the mountains don't have to do as much effort as the ones that are in the valleys, because the ones in the valleys first need to escape the valley before they can travel through the universe. So you have this kind of difference. Some photons are already at the top, they're free to travel, some are at the bottom, so first they need to spend some energy getting out of the valleys before they can travel. What this means is that when these photons reach us today, they're going to have different energies. There's going to be some that didn't have to spend energy in the early universe, so they're a bit more energetic. And then there's going to be others that had to already spend a bit of energy, so they're slightly less energetic. And what this leads to, when we look at these photons today, it leads us to the CMB. The CMB is the cosmic microwave background radiation. It is the oldest light we have in the universe in any direction we look, and it really is the afterglow of the Big Bang. Now you can see it either up here, or I believe if you're on Twitch and YouTube, it should be that side, maybe that side. Haven't yet figured that out. Anyway, this image that you can see somewhere around me, because it moves depending on what platform you're on, is the CMB, the cosmic microwave background radiation. What you can see here is that there really are these orange spots and cold spots, which corresponds to hot spots and cold spots. If I were a photon in the early universe, I'd be fine just staying where I was and never leaving. Yeah, the thing is, the photons were happy doing that, but they simply became the third wheel, right? You had the protons and the electrons, they used to be friends, and then the protons and the electrons joined up in a monogamous relationship, and the photons kind of had to break away. Now, the technical reason is that photons actually like traveling freely. They like traveling at the speed of light, and a photon will try to travel unhindered. Now, it's not so much that they were happy down there with the others, it's that they physically could not travel further because the other ones get bumping into them. So as soon as the protons and the electrons join together, the photons are actually free to continue their journey finally. And that is why they break away and start traveling. But by the time it reaches us, what we are going to see are these orange spots and blue spots. Now, the orange spots are slightly hotter, the blue spots are slightly colder. Now, here we have the idea that Let me just think 1 sec. So the ones that came out with the valley had to lose a bit of energy, so they already lost some energy. The twitch is on the right of the screen, so that way, I believe. Okay. So what you see here, the photons that left the valleys, which correspond to these overdensities, already lost some energy, which means by the time they reach us, they've lost a bit more energy, so they are blue, they are colder. Whereas the ones that were at the tip, at the mountains, didn't lose as much energy, so they're slightly hotter and therefore orange. So the blue and orange spots in the CMB, in the cosmic microwave background radiation, are related to these over and under densities in the early universe, to these valleys and mountains that we had, which were a result of the quantum fluctuations in the early universe. Absolutely amazing. We've currently got a picture that goes from the very early universe. We have these quantum fluctuations which are stretched by inflation. These quantum fluctuations set the seeds for where stuff can accumulate, because stuff is accumulated more there than on the mountains. When the particles of light break away and travel towards us, they're going to have these tiny, tiny, tiny temperature differences, which is an energy difference, but we just express in terms of temperature. Excellent question here by Scott. What's the overall difference in temperature? And this is a very nice question, because overall, the CMB is a remarkably good perfect temperature of 2.73 degrees Kelvin. So these temperature differences are of the order of 0.00001 Kelvin, 10 to the minus 5. I always have to count the zeros when I do that. 10 to the minus 5, which means it's 1 part in 100,000. So it's 100,000th of a Kelvin, so 100,000th of a degree Celsius that is different between these particles. So it's a really, really, really small difference. But the fact that we have these blue photons and the orange photons, these warmer and colder regions, really tell us that this idea of these cosmic waveforms that led to these voids and mountains is actually a believable possibility, because it really helps us explain why we see the CMB the way we do. And just want to say, I think I missed some comments there, because I get carried away with this topic. Okay, that one I answered, that one I answered. Just quickly going through all of the comments. Great one by Paul here. The CMB light we see now was 380,000 light years away when it was emitted, or 13 billion light years away. So you can imagine that the CMB was emitted at every point in the universe at the same time. It was emitted 380,000 years after the Big Bang, so 13.5 billion years ago from our perspective. Since then, these photons have been traveling freely in every direction in the universe. When we look at them today, the CMB sets the boundary of the observable universe and the unobservable universe for now. I'll get to that later, but for now. So the CMB really is the furthest thing away we can see. Now, this was emitted 13 billion years ago. So it would be reasonable to say that the CMB photons are 13 billion light years away. But they are actually much further than that. They are 43 billion light years away. So when we see them now, the actual CMB itself would be technically 43 billion light years away. The reason being that between when it was emitted and started its journey towards us, and now the universe has carried on expanding. This is why if we see a galaxy that is 2 billion light years away, by the time the light reaches us, that galaxy has moved further and further away. So even though when the galaxy emits the light, it's like 1 billion light years away, by the time it reaches us, that galaxy is 2 or 3 billion light years away. So we can kind of see further than you would expect based on the speed of light. Now, if the universe were not expanding, the observable universe, which is just the patch of the universe we can see, would be 30 billion light years across. But because the universe is expanding, it's actually closer to 43 billion light years in radius, 96 billion light years in diameter. So the CMB was produced 13 billion years ago, but it is actually about 43 billion light years away from us, which is always fun, always cool. Okay, but that was a great question, Paul. Sorry if you answered my question and I missed it because the app crashed. Okay, Scott, I did answer your question. Just to recap, the question was, what's the overall temperature difference in the CMB? We're talking about 1 part in 100,000th of a degree. So it's 10 to the minus 5. It's a really, really, really small temperature difference. So, yeah, the CMB is one of the biggest pieces of evidence we have for the fact that in the early universe we had these valleys and these mountains triggered by quantum fluctuations in the very early universe. But I promise that today we're talking about structures in the universe, and of course I've gone on a tangent for the CMB because why wouldn't I? It's the CMB. But this is actually not the main point today. This is just a reminder of one of my favorite things in the universe, but it is actually not the main point today. So, going back to our story, we have these valleys, we have these mountains. In the valleys, we have dark matter. Oh, question. Are we able to decipher what CMB would look like in far future with any accuracy? I love that question. That's a really, really, really nice question. And it's a nice question because it reminds me of a question we set in when I was tutoring or TAing general relativity. There was a question that was in the exam for the students of how long would you have to wait to observe a completely different CMB to what we see today? The answer is 10,000 years. 10,000 or 100,000? 100. I should redo the calculation. 10,000 years. Let's go with 10,000. So, yeah, what the CMB will look like in the future, it will carry on redshifting to different wavelengths. The blue and the orange photons will carry on losing a bit of energy. Now, the overall statistical properties won't change much, and that is important because we don't really care so much if one individual photon is warm or one individual photon is cold. What we care about is the overall statistical distribution of these photons. So how these photons are distributed in the sky, how many hot ones, how many cold ones. So even though the CMB will change in the future, this information, the statistical information, will still be contained, just in a slightly different range of the electromagnetic spectrum. So what the CMB will look like in the future is a more evolved version of what we have now. Now, the good thing is we have, thanks to the CMB and to a lot of other observations, we have a pretty good understanding of what the universe, or what we think the universe does. So then we can just apply that, like fast forward, this is what the CMB is going to carry on doing in the future. So we do have pretty good ideas of what the CMB, how the CMB is going to behave, because the idea is it's going to continue behaving in the same way that it's behaving now, we hope. So yeah, back to our story. We have these valleys, we have these mountains, we have the dark matter in these valleys, which attracted a few things. The photons broke away. So now in the valleys, what you have is a lot of dark matter piled up and a lot of hydrogen piled up. And the cool thing is, when you put enough hydrogen in one place, you can actually start forming stars. You put enough hydrogen in a dense space, you compact it enough, you can start stellar fusion, and you can start forming the first stars. Fusion, yes, fusion. I always mix up fusion and fission, and my way of remembering it is to remember in Dragon Ball that they do the fusion dance, and it's two that go into one. So fusion is when two people go into one, and fission is when you split. And every time I talk about fusion and fission, I have to remind myself of Dragon Ball. It's my way of remembering it, which is sad and weird, but also funny. So yeah. If you put fuse together, exactly, but I know it makes sense if I think about it, but I always have to go via Dragon Ball for it to actually make sense. So at least I don't start doing the actual fusion dance. So that would be weird. So yeah, if you put enough, just completely distracted myself there. If you put enough hydrogen in one place with enough density and enough pressure, you can actually start the first stars. So the first stars actually began to form in these valleys that were left by the quantum oscillations in the early universe that were stretched during inflation. So now you have dark matter and galaxy and stars starting to form together. And once you have dark matter and stars together, you can actually form the first galaxies. And once you have galaxies, you put enough galaxies together, you can form clusters of galaxies. So structure actually started to form in these kind of valleys left by the cosmic fluctuations in the early universe, which is really cool when you think about it. If this is true, if what I'm saying is true, then when we look at the universe today, we should see region. Hey, it's great to see you, and good evening to you as well. So nice of you to drop by. I'm not even going to attempt to say hello in Finnish. I can say hello in Finnish because that's terve, that's easy, and I can also say hey, which is fun because I use hey for both hi and goodbye, which makes it so much easier. And I can order a cinnamon bun in Finnish, which is all I need to do, basically. So if what I'm saying is true, that you have these valleys where galaxies begin to form, then when we look at the way matter is distributed in the universe today, we should see this. We should see this effect. We should see that there are regions where you have more matter and regions where you have less matter. We should see kind of a structure forming in the universe where there's preferred regions and less preferred regions. And obviously, this is exactly what we do see. The most words in Finnish ordering food is the most important thing. Like if I can order a cinnamon bun and a coffee, that's kind of all I need, right? Okay, so what I'm going to show you now is a simulation. It is not real data. This is a simulation of what the universe should look like if everything I've said is true and based on all of our current understanding of dark matter and of how matter behaves. Press the wrong thing. Okay, I should get back to the chat now. Yeah, you don't speak Finnish, not even a single word. Yeah, it's a difficult language. But I appreciate you greeting me in Finnish. I do appreciate that. So what you can see up here, or that way, is what we expect structure to look like in the universe based on our understanding of dark matter and our understanding of these valleys and mountains in the very early universe. So this is a simulation of the cosmic web. Every dot in this simulation corresponds to a galaxy. What you can see is that the galaxies form this kind of web-like structure. So you have the darker regions. So the brighter the region, the more density in this image. The darker the region, the less density. So you can see we have regions where there's not much matter, these darker regions, and we have regions where there is a lot of matter, these kind of galaxies. And this is a simulation of how dark matter should fall. Now we know that there is 5% more there is 5 times the amount of dark matter as normal matter. So in the universe you have 5% normal matter, 25% dark matter, and 70% dark energy. So dark matter is much more abundant than normal matter. So this simulation here is where all of the dark matter should fall on the corresponding densities. Now, the normal matter in the universe, the galaxies in the universe, should follow the dark matter because of the gravitational force. So this cosmic web structure here is what we'd expect given these quantum fluctuations in the early universe, given our understanding of dark matter and the amount of dark matter we expect. So this really is a simulation of what we expect the universe to look like. And I do see there are a couple of people here making the comment that this does very much look like the network of neurons in the brain. That is completely true. This does look very, very similar to how neurons are distributed in the brain, which is really, really fascinating. Personally, I don't think there's a deeper meaning to it other than this structure is an energetically favorable structure. So it's one that makes sense for particles to form or for things to go into this structure because it energetically is favorable. But it is really cool to think how similar this is to a brain. In fact, Ian McLaughlin, anthropoid here on HAPS, and myself have actually talked about this in depth. We did a stream where we mentioned this once. It's really cool. So a question from Scott here. Can't remember if I asked it or not. You can always ask it again anyway. Does anyone hypothesize that dark matter and baryonic matter can literally exist in the same place, just overlaid in a higher dimension or something? That is a great question. So there are some models of dark matter which rely on extra dimensions. So the idea being that dark matter might come from some dimensions that are rolled up in a way where we can't really access them, but that would still be there. It's like if you put an ant on a piece of paper, that ant is only going to see two space dimensions, right? Left, right, forward and back. It's not going to know the up and down dimension if there's no way for it to go up and down. Now, the same argument could apply to us. Maybe we see 3 spatial dimensions, but there's actually more. They're just in a way that we can't access them. So there are some hypotheses for dark matter where dark matter is like a rolled up dimension, where you have these dimensions that are rolled up in a way that acts as dark matter, but it's actually just a rolled up dimension, which is kind of cool. So there are ideas that not drinking enough. There are ideas that you could have dark matter just being extra dimensions, which is really cool to think about. Okay, another very good question here by Paul. In 13 billion more years, how will this web look different? Great question. So then we need to think about the expansion of the universe. Now, the expansion of the universe is pulling everything outwards. Now, at the level of individual galaxies, the expansion of the universe is not enough to pull galaxies apart yet. If the expansion of the universe increases, if the accelerated expansion increases, eventually we could potentially pull galaxies apart. But for now, the overall structures will keep expanding. I think it won't really be noticeable in the overall structure of the universe, though, because everything will keep expanding. So the voids will get bigger, but so will the individual galaxies as well. So everything is kind of going to keep growing. I think the voids might actually get slightly bigger, but I'm not completely sure. I think No, I think overall the large scale structures should not change too much as we evolve in time, other than more small structures appearing, because structures do form hierarchically in the universe, or first you form larger ones and smaller ones. So more structures will gradually appear, but I don't think the overall statistics are going to change. I hope that answers your question. A short answer, I don't think it will look overly different. So, yeah, this is the simulation of what we expect matter to look like, assuming what everything I've said today is correct, and assuming our knowledge of dark matter is correct, and our knowledge of how things interact in the universe. What I'm going to show you now is actual real data. So this here was a simulation. This was the Millennium simulation. And now I'm going to switch to real data from the Sloan Digital Sky Survey. So what you can see here is actually real data. So every glowing dot you see on the screen here corresponds to a galaxy. I need to resize my images because HAPS no longer resizes them properly. So every glowing dot you see here corresponds to a galaxy, and this is real data. So the Milky Way lies along the plane at the center. Can I actually take myself off these days? No, I cannot take myself off screen. Okay, doesn't matter, I can't make it full screen, sorry about that. So the Milky Way lies at the center. The two black triangles correspond to where we have the disk of the Milky Way. Now, the disk of the Milky Way blocks out a lot of light, so we cannot see galaxies as we look across into the arms of the Milky Way. So the glowing dots you see are when we look up and when we look down from the Milky Way. And every point here corresponds to a galaxy. You can see here that we really do recover the cosmic web structure. You have these filaments, you have nodes where the filaments cross, and you have voids. So there really is a very good overlap with what the data is showing us. So the Sloan Digital Sky Survey collected data from many, many different galaxies. I think they had a couple billion galaxies by the end. No, not billion, sorry, a couple million galaxies. And you can really see the cosmic structure here. So is it the first I'll answer the question from Paul here. The labels around the edges of the circle look like time. Yes. So often when we talk about position in the sky, we we use right ascension and declination to find positions in the sky, and the time just gives you the overall angle in the sky. So we break the sky into like 24 hours, and we use that to find the position of objects. So this is really just giving you the position in the sky relative to the Milky Way. So it is phrased like hours here, but it's really just about the overall position in the sky. It's what we call galactic coordinates. No, oh, I've forgotten the name. It's the coordinate system we use to find things in the night sky easier. And my astronomy is really slipping. There used to be a day where I could do that without tripping up on those words. So yeah, the labels around the edges are about the hours, which just tell us where to look in the sky to find these galaxies. And you can also see the redshift here. This goes out to a redshift of about zero 0.1, which should be a distance of 2 billion light years away, I believe. Then there's a question from Abyss here. Is there a plan to position CMB telescope beyond the L2? So WMAP and Planck were both positioned at L2. And I don't think there's a plan to go further because you wouldn't really gain much. So in terms of the temperature anisotropies of the CMB, so the temperature differences, we already have remarkable position. Now we're pushing on polarization and lensing, but I don't really think you would gain much from going beyond L2, other than it would be very difficult because it's always expensive to move things even further. Then you have the problem of powering it because you no longer have as much solar power. So L2 is a good place to put these CMB missions. There are ground-based ones currently. There is an idea, potentially, hypothetically, of placing a CMB mission on the far side of the moon, which would be cool. But I'm not sure how feasible that one is. Yeah, David Dunn, astronomy professor here in the comments, just reminded me this is called the right ascension. It's not the declination, that one is an angle. It's the right ascension that gives us the hour times here. And this is, of course, inside the solar system. So here's the real data. Yeah, this is the real data. Question from Scott here. Was the Just Wonderful Space Telescope fully deployed? It was. Like, everything went so well. The sun shield deployed, the mirrors deployed, the mirrors are now getting into position, and tomorrow it reaches L2, and everything has gone so remarkably well that it's amazing. It's gone so well that it's quite likely that there will be several more years of mission than initially planned because they didn't have to spend any fuel doing anything. So yeah, it's really cool. Once you get into space, it seems silly to go back down into another gravity. Yeah, but the idea of going on the far side of the moon is that you're completely isolated from the sun. Right? It's very cold, and it can be very good if you want your telescope to have absolutely no influence from the sun. The dark side of the moon is going to be dark. So, is that correct? Is my statement correct there? Yes, that should be correct. I just got slightly confused by something there, but yeah, you do lose something by going. Dark side of the moon is not always in the shade. No, you completely block out the Earth. I'm sorry, you completely block out the Earth if you're on the far side of the moon. Yeah, obviously, that's what I was just thinking. The far side of the moon does see the sun. It doesn't see the Earth. Yes, sorry about that complete brain fart there. Yeah, if you position something on the far side of the moon, the advantage is you completely block out any signals coming from Earth, but you do still get the ones coming from the sun. For a CMB mission, it might not be so great, but one thing that would be very nice is a radio mission, because then you'd block out all of the radio signals from Earth and anything coming from the Earth, and you would still get some sunlight periodically, but you completely block out any signals coming from the Earth. So there are ideas to put stuff on the far side of the moon. I don't think any of those are really past the funding stage yet, but they are cool missions. But yeah, then now, if we want to get more position on the CMB, sending something outside the Milky Way might help, but that's just not really difficult. We've only been able to send 2 things outside of the solar system, and it's just very difficult. Sorry, solar system, not Milky Way. Brain is not working. Okay, yes. If we wanted to observe the CMB better, if we were able to leave the solar system, we'd be completely clear of a lot of systematics. It would be a lot easier, but it would also be very difficult to get something. We've only been able to get 2 things outside of the solar system, which are the 2 Voyagers. So it's very difficult to get something outside. So a CMB mission outside of the solar system, I don't think it would be economically viable. And I don't think it would improve our understanding enough to convince funding agencies to fund that. So sorry about that. Brain just got a bit confused with 2 topics there at the same time. Okay, the Just Wonderful Space Telescope is indeed living up to its name, if we accept that that is its proper name. So, yeah. New Horizons has noticed a difference out there. Yeah, exactly. Going out beyond the solar system would be cool, but I don't think it's economically viable. So, yeah, Voyagers 1 and 2 only left very recently. So, yeah. Who volunteers to go out and repair the mission that's outside the solar system? It would be pretty difficult to get there, right? I mean, already the ones at L2, currently we can't repair them. If there's something at L2 that just breaks, it's just like, meh, okay, it's broken. Maybe in the future we'll get to it, but currently we can't. Okay, went off on a few tangents there. I want to go back to the structures in the universe. So what you can see in this image, or that image, is the overall distribution of matter in the universe, and this is the real data. So every dot here corresponds to a galaxy. And you can see that it really, really does fall along the cosmic web. So this really leads to the idea that the story I've told today is correct, that we had these quantum fluctuations that were stretched. This left valleys and mountains in the early universe. Dark matter clustered in the valleys. This pulled everything together via the gravitational force. The CMB gives us evidence of these mountains and valleys, and it sets the seed for structures to form in the universe. So the same mechanism that gave us the CMB is what actually allowed galaxies to form. So these quantum fluctuations in the early universe are the source of structures in the universe today. And what I'm showing you here is a still image from the Sloan Digital Sky Survey. But I do actually want to show you a different image, which is the 3D map from the Sloan Digital Sky Survey. And because I cannot upload videos yet, we're going to do this with screen share. So bear with me a minute as I try to figure out the screen share today. Select screen to present. This should be easy. I think I've done screen share before already. So let's see. Let's see if I can get this to work properly. You should now see something coming up in the screen, which let me just zoom in a bit here. Okay, how is this going here? Good enough. Let's make this full screen. Okay, so what you should be seeing I either have the Chrome window open or I have apps open. I don't have both open. So what you can see here, I hope you can see it moving. This is the 3-dimensional images from the Sloan Digital Sky Survey. So again, the Milky Way is along the 2 black triangles, and then we have all of this structure forming around it. So we do really have this cosmic web structure as measured by the Sloan Digital Sky Survey. And I really hope the image was moving for you. because I have to change tab. I either see the moving image or I see HAPs. I don't see both at the same time. So here you really, let's just make it move one more time. Here you really can see the three-dimensional structure as measured by the Sloan Digital Sky Survey. It's pretty cool when you think about it. And it really does give more to the idea that we have this cosmic structure in the universe. So it's really cool that the Sloan Digital Sky Survey was able to see that. Okay, obviously because I changed screen, I just missed a few comments. It works great, thanks. Audience tip, on a Mac, you can use the trackpad stretch gesture to zoom in on that image. Thank you. Yes, of course I could. I could have just done that myself. Okay, perfect. So that was a three-dimensional sky map we have from the Sloan Digital Sky Survey. And that's already pretty impressive, right? Let's just recap here, because I'm always amazed by this story. We had quantum fluctuations in the early universe that had a wavelength. This was stretched as the universe expanded. This left ripples in the fabric of space-time, or signatures in the fabric of space-time, where dark matter could fall in the valleys. This then triggered CMB to decouple and produce the red and blue spots, the hot and cold spots that we see in the CMB. And because dark matter and then hydrogen clustered in these valleys, the first stars could begin to form, galaxies could form. And today we can test this by looking at this cosmic web in the universe. So we can tell the story from the very early universe to structure formation through the CMB, which is incredibly amazing when you think about it. It's so cool that we can tell this story. It's really cool. Is it fair for me to think of the ripples as gravity, or is it just a pattern like a wave pattern? I think both. So there's like the bisexual answer to everything, like both. Sorry, it's a completely off-topic joke there. I just had to make that joke up myself. I'm realizing that the problem with my new time for the streams is that my brain is already getting into sleep mode. So this is fun. Yeah. So these ripples, they're not really ripples in the same way that gravitational waves are. They're this waveform that is stretched affects what we call metric fluctuations, and this imprints as a density well. So you do have these gravitational fluctuations, but they are not caused by gravity themselves, but rather they kind of source a gravitational potential. So you have these ripples, or this mountain and valley, and this causes regions of overdensity where dark matter can accumulate because of the gravitational force. So you do have the intricate balance there. But yeah, I think both is a good answer to that question of whether you should think of it as gravity or just ripples in, like folds in the fabric, not really folds, overdense regions in the fabric of space. It kind of goes hand in hand there. So I'm laughing at myself here. So yeah, this is a really cool story, and we have this data from the Sloan Digital Sky Survey, which is amazing. But it is not the end of the picture, because there are more telescopes out there that want to expand what the Sloan Digital Sky Survey did and look at more galaxies. And there's one instrument that I really like, which is called the Dark Energy Spectroscopic Instrument, DESI, which is something that has been built for a few years now, and it began taking data in the middle of 2021. Now, DESI is a mission that is going to help us shape our understanding of dark matter and dark energy. And to do this, it is trying to measure 35 million galaxies. So it's doing a sky map very similar to what the Sloan Digital Sky Survey did, but going further, looking further back in time. DESI, exactly, Dark Energy Spectroscopic Instrument, DESI. Now, DESI had a few delays, but it actually began taking data 5 months ago. And this is really cool. It's planned to be a 5-year mission. So it's only slightly into its mission. It's going to be taking data for 5 years. And it is currently accumulating 1 million new galaxies per month. So every month, this is a ground-based telescope, and every month it is able to catalogue 1 million galaxies. And for each of these million galaxies, it gets the redshift and the distance. So it is really constructing this, not the distance, sorry, the redshift. The distance would be amazing. It gets the redshift of all of these galaxies, which means it's able to construct a 3D map very similar to the one that I just showed you for SDSS. And here's the cool thing, and why we're doing this topic today, and I'm leaving this for like 5 minutes before the end to actually get to my point. The DESI instrument released its first data 5 days ago. So at the beginning of this week, we got the first images from DESI, which is really cool because I didn't know that was planned. I thought they wouldn't release data for a while. So there's not been so much on the side of dark matter, dark energy analysis just yet. Thank you for the Heart Bomb Award. Thank you. I do appreciate all of the awards here. So it took me 55 minutes to get to this announcement, but DESI released its first images of this 3D structure of the universe 5 days ago. So we absolutely do need to go and see these. And just give me 1 sec to get the image ready, because now I've completely lost my screens, which is not good. And the thing is, the dark energy spectroscopic instrument has not just released one still image, it's released a 3D slice moving through the universe, which is cool, but also means that once again I can't upload it. So we are going to once again go to screen sharing. So bear with me while I get the screen sharing ready again. And it should be this one here. And let's see, let's just bring it over here a bit so I can actually see both. And let's scroll down a bit here. Okay, I'm not sure how well this is going to render here on the screen. Let's see. I hope you can see it. It looks a bit pixelated, unfortunately. But I'm not sure how well you can see this on your end, so I'm just going to send a link to the chat as well. For now, I will only be sending the link in the HAPS chat, but I will add it onto YouTube and to Twitch later on as well. But let me just... Now I have the problem that my stop sharing screen is covering the way to get back to my chat. Bit annoying, but okay. I'm not sure how well you can see this image. I hope you can see it. The shimmering that you see is as it moves across and highlights different galaxies. It's really, really cool because they've already catalogued quite a few galaxies. They've already catalogued 5 million galaxies up to a distance of 5 million light years away. 5 million? Yes. And it's really 5,000 light years away, right? Let me just check. No, 5 billion light years away. Okay, yes. So they've already catalogued galaxies up to 5 billion light years away. I'm not sure how much you can see the shimmering here, but it really is cutting this wedge across the sky. If you're following on HAPS, check out the link I sent you. If you're not following on HAPS, I'll post the links on YouTube and Twitch after the stream has ended. But if you search for Dark Energy Spectroscopic Instrument, first data release with DESI first images, you'll find this. And I also want to show you another image. Again, we're on screen sharing here. So this image, the first one you can see here, is from the Sloan Digital Sky Survey. So every data point that was mapped out by the Sloan Digital Sky Survey. And after just 5 months of data taking, this is what we have from DESI. So you can see here, I'll just do this again. This was the Sloan Digital Sky Survey. This is DESI after only 5 months. And you can see that it's already got a whole new chunk of galaxies that we didn't have before. One more time. This was the Sloan Digital Sky Survey. This is what we have now with DESI. You can see that we really, really have expanded the amount of galaxies. And again, this is just in 5 months of data taking. So this is only 5 months into the Dark Energy Survey. Yeah, if you want to search for this, please do the search for like Dark Energy Spectroscopic Instruments, because DESI, of course, means a lot of different things to different people. So yes, do search for DESI Dark Energy, and then you will find these new images. I did post a link here. And it's really cool to think that in just 5 months of data taking, the DESI spacecraft might not work because it is a ground-based mission. This is a telescope. But if you search for DESI telescope or DESI Dark Energy, you will find this. I do have the link here in HAPS. I will post a link on Twitch, on Twitter, and on YouTube as well when the stream is over. But it's incredible to think that in just 5 months of data taking, it's already got more galaxies than SDSS. Now, of course, they have slightly different purposes, but it is a really new telescope that is taking data and that is going to revolutionize our understanding of dark matter and dark energy. So once it gets 35 million galaxies, it will really be able to map the time evolution of dark energy. So it's going to tell us a lot about how dark energy behaves and how dark matter behaves. So it's really exciting, it's really interesting. And I did not know that it was planning to release data so soon. Like I was just checking the news on Monday or Tuesday and saw the notification of new image of galaxies. Like, whoa, we have a new sky map. Nice. So yeah, that's the reason for the stream today. Thank you for the love, but I do appreciate all of the awards you send me. So yeah, it's really cool. We have this mission that is mapping the cosmic structures in the universe. And again, a reminder that these cosmic structures, these filaments, this cosmic web, we can explain from quantum fluctuations, we can tell the story from the early universe, quantum fluctuations going through the CMB to the galaxies we see in the night sky today, bringing everything in the universe together. It is really, really cool. It is my favorite story to tell about the universe. And we have data that backs it up from the CMB and from the large scale structure. We have telescopes that are pushing our understanding of the distribution of galaxies further, that are helping us really get better images, get more understanding. And I think within the next 10, so it's not the only one, there's 3 or 4 other upcoming telescopes or satellites that are going to push our understanding of dark matter. And I really think the next 10 to 15 years are going to change our understanding of dark matter and dark energy. The next 10 to 15 years are going to be make or break for the standard model of cosmology. I'm confident, not that we will find dark matter or dark energy, but that within the next 15 years, we will understand more about dark energy and dark matter, and maybe we'll reach a conclusion that we've been wrong about both of them, maybe not. But I really think the next 10 years are the time for large-scale data of the universe. It's an exciting time. It's really an exciting time. There was a broad question from James just now. Are all the data from all these telescopes probes distributed to general world, or do you hear restrictions? So very much depends on the satellite and on the mission. For example, the data from Planck is publicly available. All of the Planck data is available. You can go from the raw Planck data to the process run, the whole cleaning step, it's all publicly available. The Sloan Digital Sky Survey is publicly available. I think its successor, EBOS and BOSS, I don't think that's publicly available. I wish it were, because I kind of like to use it. But not all of it is publicly available. Some satellites or some telescopes have the thing where they have like an embargo for 5 years where the scientists first get the data and then it's released, which I think is fair. But I do think all data should eventually, and not too long, be made publicly available. I'm not actually sure what the DISY policy is in terms of their data release, so I cannot answer what DISY specifically is doing with their data. As said, this image came out 5 days ago. I haven't really gone into the details. I just thought, like, I need to do a hacks about this. Okay, DISY is in Arizona. Yes, thank you. So there's another one in Chile, and I talked about both of them on Friday. And I didn't want to say Chile or Arizona to mix them up, but if you say Arizona, I'll believe it. It is definitely going to be the Arizona one. Yes. So DISY is in Arizona. There is another one ongoing in Chile as well, which is the Dark Energy Survey. So data cleaning is a fun job indeed. It's fun. Let's leave it at that. You always have so many things, so many background signals, so many noises, so many things getting in the way of the data. Yeah. I mean, I'm glad that the actual data cleaning is not directly my job, but also I do have to do some fun things of asking what things are going to cloud my data, which is fun. So this was the topic I wanted to talk about today, because we have this new map from the Dark Energy Spectroscopic Instrument, and it's really cool. And it gave me an excuse to tell a story going from the CMB right through structure formation and touching up on quantum fluctuations. And every time I do this, like today I spent an hour doing this, I'm reminded of how strange it was that I did this whole story in a 3-minute science slam some years ago. I did a science slam, which was fun. I was given 3 minutes to explain a story about my research, and I chose to explain this story of quantum fluctuations through inflation and structures and CMB in 3 minutes. There was way too much packed in those 3 minutes, but if anyone's curious, that video is actually on YouTube. If you search for a fingerprint of the universe, or if you search for my name on YouTube, you'll actually find it. It was fun. It was terrifying because I got on stage in front of 400 people. It was one of the things that actually helped me get used to public speaking. Absolutely terrifying. But it is on YouTube if anybody wants to laugh at me getting a slinky toy stuck. So, aside there. So it's been great fun today. That was the first appearance of the slinky toy. Indeed, that is when because we could bring one prop to the science slam. So I brought a slinky toy, and my slinky toy was the one that told the story. And then at some point I put the slinky on my wrist, and then it got stuck. And you can see at some point in the YouTube video that I'm trying to get my prop back so I can do the second part of the story and then give up. And then one of the comments I got from the judges is, you didn't use your slinky toy enough. It's like, yeah, it got stuck. Sorry. That was funny. Was I speaking faster than I was now? Yes. Actually, these days, I know I still speak a bit fast, but I'm substantially slower than I was in the early days of streaming. Like recently, I've been going through all of my old streams, and I actually have almost all of them saved. Now, not all of them, because there's been some issues with some, but I have a lot of my previous streams saved. And I went back and watched one of my first streams that I ever did. It was so bad. Like, I was talking so fast, I was stumbling over words. But just the first year of my streaming, I was speaking too fast. And now, if you think I'm speaking fast now, I can assure you I'm about half the speed I used to be in my streams. People who have been around for 6 years will probably know that my speed has improved. Now I try not to go so fast because it's just pointless. But in the science slam, I did speak rather quickly. But it was fun. It was a fun experience. I don't have any regrets about the science slam. I didn't progress to the second round, but that's fine. I really enjoyed it, and I'm not going to do that again, but I did really have fun, yeah. Your brain slowed down the same amount so you didn't notice. Good reason, good reason. But no, I have definitely slowed down. But yeah, some of you have been with me for over 6 years now, and I do really appreciate all of you. 6 years watching me almost every week. I love that you keep coming back and chatting to me and asking questions. Those of you who've been around for so long, it's great to see you. It's like people I've known here for 6 years through my streams. It's amazing. So yeah, you consistently have to remind yourself to slow down when you talk. I do too. Now I've got used to it. Actually, what got me used to it was working with kids who didn't speak English as a native language, and I was there teaching them English, because then I had to speak slowly, just because we were teaching the kids a language they didn't know. So I had to speak slowly, and that actually forced me to slow down. But yeah, I know today I sped up a bit because we were talking about the CMB and structures in the universe and all of the things I love. So I know I went a bit fast today. If at any point you think I'm speaking too fast, just let me know, and I will make an effort to slow down. That is always the case. So this brings me to the end of the last stream of the first version of my streams. So for anyone who missed it at the start, next week there's a new relaunch after, or the biggest makeover my streams have had. After 6.5 years, I finally decided to improve my streams, to unify them a bit more. So you might have noticed the last 2 weeks there's been the title already. The streams are officially called Cup of Cosmology. So next week I'm doing the real launch of Cup of Cosmology. You can expect a web page. The YouTube channel was up and running today as a test, but the YouTube channel, I can actually already tell you there was a lot of stuff on the YouTube channel that is currently unlisted, and it's just one click away from going public next week. The web page is also a bit more than one click away, but it is on its way to going public. So next week you can expect a web page, you can expect the YouTube channel, but everything will be announced, advertised here in a live. So I'm going to do the launch live. I'm not going to click the go live button when I'm live on my website, but essentially we will do the launch together. So next Sunday, 8 p.m. Helsinki time, which is the same time I started today, so 1 hour less than what it is now, I'm going to start the new Cup of Cosmology adventure. And I really hope you'll join me for it, because I'm looking forward to sharing it with everyone. So some nice comments here. You never thought cosmology would be an obtainable subject. Well, I'm glad you've been around. I know, James, you've been around for many years as well, back in the TTK days as well. And I appreciate you coming back every week, or nearly every week, whenever you can. I appreciate you all being here. David, Paul, Scott, all of you, I really appreciate you being here all the time. Okay, makeover sounds like cosmetology. Yeah, maybe I'm finally going to cosmetology. Don't worry, I'm not. And Scott, your jokes will still be perfectly acceptable. There will actually be rules listed on my webpage, but nowhere does it say that jokes are not allowed, and jokes are always encouraged. Thank you for your comments, Abyss. Yeah, it's you missed the TTK scopes. The TTK scopes were fun. The TTK scopes is when I went on a tangent and started a second account at my institute and convinced a lot of people to join me. And it got to the point where they actually carried on without me as well, which was really nice, because else I was doing it twice a week. The 3 or 4 people who were doing the TTK streams are no longer at the TTK. They've all left. Everyone in academia moves on to different places. Some of them are no longer in academia, some are. But I have had a couple of the TTK guests join me on this channel. Maybe I can get a few more. Maybe I can bring back some more of the TTK people, because it was always good fun. But I also have a lot of people at Helsinki who have volunteered, who I have asked repeatedly to be on my streams and might be on my streams soon. So yeah, going forward, more guests, easier to ask me questions, easier to request topics. I do want to mention something that I think is important, just for the full sake of, in full transparency. So up until now, all of the awards I've received on hats, all of the money I've received on hats from sponsorship and awards, I have donated. And that is going to be true for everything I get up until the end of the stream today. Then from next week, that is no longer going to be the case. Instead, with my webpage, there will be a direct way where people can either choose to support me or to support the charities that I care about. Anyone who chooses to support me, the money will go to maintaining the streams and Cup of Cosmology. So, full disclosure here, everything anyone's donated up till today with the sponsorship and awards, I really appreciate it. That will all be donated because I've committed to doing that. But from next week onwards, that will no longer be the case. So, from next week, any money that I get through hats will go to maintaining the streams, but there will also be a direct way for people to contribute to charities that I care about. You'll see more next week, but just in the sake of full disclosure, from the next stream onwards, the money I get on hats will no longer be donated. So just being very clear about this, it will also be stated very clearly on the webpage. There's a webpage coming. So do really appreciate everyone who's sponsored me, everyone who's given me awards. I really do appreciate it. It always means a lot to me. So I'm looking forward to the relaunch next week. 1 week to go. I have so many things to get ready, but launch is happening next week. 1 week minus 1 hour from now. So I hope to see you all then. And I hope in the meantime,